I think we can now go to start the session. Okay. So good evening, everyone. Welcome to the workshop on pharmacophore modeling. Basically, it will be a hands-on workshop as well. So, in the initial phase, I will be presenting you about the basic information about pharmacophore modeling. Okay. So, what exactly is pharmacophore modeling? What are the different, you can say, descriptors that we are going to study in pharmacophore modeling, and different sort of pharmacophore techniques and all that thing. Okay. And later on we will be demonstrating pharmacophore modeling, basically structure based pharmacophore modeling using Pharmit. Okay, so Pharmit is a web server. You can easily get access to that, and then you can perform, you can say, virtual screening of different compound libraries. Okay, you can even create your own libraries there and then screen your compound molecule. Okay, so let's get it started with the presentation, and later on I will carry further for the demonstration. Okay, so let me introduce myself. So I'm Suman Dungal, running Nepomics Biotech from 2021, and we have been organizing this sort of, you can say, virtual internship as well as workshop and webinars and even some tutorials and this kind of things. Okay, especially focus on computer drug designing. So you can go through our social media, our YouTube, or you can even visit our website for more information. Okay, let's let me present the thing now. Okay, so let's get it started. So previously we have organized molecular docking as well as QSR session. Okay, we have built QSR modeling, 2D QSR modeling, and then we validated it and tested with our derivatives. Okay, you can check our previous you can say workshop videos on YouTube, and we have also done molecular docking of aspirin derivatives. Okay, or you can say simply aspirin in cyclooxygenase receptor, cyclooxygenase 2 receptor, and we have validated it as well. You can go and check that. That has been already uploaded. And carrying further, we will be doing pharmacophore modeling, especially not in, you can say, cox receptor. We'll be doing on you can say acetylcholinesterase, that has been already published. Okay, published by us from Nepomics Biotech. So it will also give you a more insight into the validation work as well. Okay, taking further into molecular docking, the pharmacophore modeling, taking into the molecular docking. Okay, so and next is we'll talk about pharmacophore. Okay, what pharmacophore is. Okay, pharmacophore modeling as well as different core features of pharmacophores, and then you can say the type of pharmacophore modeling, or you can say approach in pharmacophore modeling, ligand based as well as a structure based, just like molecular docking. Okay, we can perform drug designing, or you can say molecular docking based on, you can say, ligand information, or you can say receptor information. So similar to that in pharmacophore modeling as well, we can take ligand as well as a structure. So today we will be doing a structure based modeling. Okay, so later on in the second half we will be doing a live demonstration session of acetylcholinesterase and its inhibitor, particularly one QTI would be the receptor. And because I've taken one QTI because we have already published that in that molecular docking and molecular dynamic simulation, as well as you can say in silico pharmacokinetics work on ACHE, acetylcholinesterase, in the particular receptor. Okay, one QTI. So I will be taking that into further study, and then screening many different inhibitors from the database. Okay, along with my own compound. Okay, so next is we'll be also discussing about application as well as key takeaway from this workshop. So let's get it started with you can say the introduction of QSR. Okay, so first of all, let's do the recap thing. Okay, for previously we have done QSR modeling, so we have built a 2D QSR model. Okay, using aspirin derivative. Okay, okay, I have taken a different sort of aspirin derivative that has been already approved by FDA, or they were in clinical trial. Okay, and then we have taken that into for the consideration to build a model. Okay, and then screen our own derivative. Okay, using different regression analysis, as well as the IC50 value was converted into PIC50 values and all that thing. Okay, you can get the information. You can visit that particular video as well. Okay, so let me get it into two more participants. Okay, they are online. Let me check that. Okay, let me come back. I'm not seeing them right now. Okay, so for that we have built it and tested onto our derivative, okay, particularly on QSR modeling. And in case of molecular docking, the same aspirin molecule was docked into COX receptor, although it was just a training set, okay, but you can get the basic information of molecular docking there using Autodock Vina with Chimera, okay. And later on we'll be also doing molecular docking using Discovery Studio Visualizer along with the integration of Autodock tools and Autodock Vina, so that you can easily get the hydrophobic interaction for that purpose as well, okay. And for pharmacophore modeling, today we will be extracting the information particularly from one QTI, that would be acetylcholinesterase receptor, and then we will find the key features, okay, key features of parent ligand, so that the similar features would be applied to our ligand of interest, okay. So if you are screening any kind of ligand molecule or any kind of compound molecule, the similar spatial feature, then you need to get that particular one, okay, so that you can go further into molecular docking with much confidence, okay. So let's talk about pharmacophore. Okay, so pharmacophore, you can see the IPAC definition has been written over there. So it is an ensemble of, you can say, static as well as electronic features. Okay, there are a lot of this kind of features that needs to be present in a particular you can say molecule to have that biological impact. Okay, so that kind of you can say electronic or spatial static features are considered to be a pharmacophore. Okay, and in other word, you can say pharmacophore is not a real molecule. Okay, it's not a molecule, but it's the feature of that particular molecule, that particular active molecule that binds into the particular site, you can say the particular active site of that receptor to have that biological response. Okay, so you need to have that particular features in your ligand molecule as well. So the importance of pharmacophore modeling that you can see on the screen as well, virtual screening. So you can screen huge number of compound molecules by you can say creating your own model. Okay, first of all, you need to prepare a pharmacophore model. Okay, you need to get the basic insight of what different you can say pharmacophore features are there in a particular molecule, and based on that information you can screen you can say plenty of compounds. Okay, millions of compound in a single click. Okay, so next is scaffold hooping. So if you are familiar with the scaffold, then scaffold is you can say a basic structure of a compound molecule, and with that scaffold we can add substituent or function group to create a new molecule. Okay, derivatization, all that thing. So even if you have a different kind of scaffold, if a molecule carry a same function group or similar kind of spatial features, then you can still screen that molecule. Okay, so what I particular mean is that even if the scaffold is different, you can still screen your compound molecule for the further analysis. Okay, like you can say biological activity prediction and all that thing. Okay, even molecular docking and leading on to dynamics. Okay, so that is the major importance of pharmacophore modeling. And next is lead optimization. So once you create your model, you will go on to screening your own compound molecule and then go for molecular docking, and then you will be optimizing your molecule based on that information, and you will be generating your particular lead molecule. Okay, so that is why pharmacophore modeling is important. And next is you also get an idea about understanding the structure activity relationship of your compound molecule. Okay, what different functional group are involved to have that particular biological property and all that thing, you will get that from pharmacophore modeling. Okay, so there are different sort of features in pharmacophore, or you can say different sort of chemical features are involved in a particular compound molecule to be a active molecule in binding into the active site of a receptor. So among them, you can say hydrogen bond donor, hydrogen bond acceptor, hydrophobic regions, okay, aromatic ring, positive ionizable part, negative ionizable part. These are the basic, you can say, pharmacophore features. Okay, so in case of you can say QSR or even ADMET analysis, we have already discussed about molecular descriptors. Okay, like what would be the hydrogen bond donor number, okay, hydrogen bond acceptor, okay, and a lot of things were already discussed over there. You can say rotatable bond, number of rotatable bond, okay, and these all are the things. Okay, and aromatic ring, number of rings present in a particular molecule. Okay, so these are the key features in pharmacophore. Like in case of hydrogen bond donor, you can see the groups like OS group, NS group, these are particularly important to, you can say, donate a hydrogen bond. Okay, similarly in case of you can say hydrogen bond acceptor, C double bond or carbonyl compound, carbonyl group are important for here. Okay, in case of hydrophobic region, you'll get a lot of non-polar areas. Okay, that favors van der Waals interaction. Okay, and similarly the aromatic ring. Okay, aromatic ring particularly focus on hydrophobic interaction, especially pi interaction. Okay, pi sigma bond interaction, all these kind of hydrophobic interaction. Whereas positive ionizable part, like you can say N plus, you can say amino group or something like that. Okay, these group carry a positive charge, okay, at physiological pH, and they are very important in, you can say, protonation as well. Okay, next is negative ionizable. So different sort of groups are present over there. They carry a negative charge at physiological pH, and that are very active into the core features. Okay, so next is you can say two different bases, or you can say the type of, you can say, pharmacophore modeling. Okay, one is ligand based and another is structure based. So in case of ligand based, you will have a different set of ligand molecule. Okay, known ligand molecule, they are already active in that particular you can say they are particularly active into the active side of that particular receptor. Okay, carrying you can say specific biological property. Okay, so you need to have that set of ligand molecule first. Okay, and then you can screen, you can align that ligand molecule, superimpose that ligand molecule, and find the particular features. Okay, what different features are important for okay, executing the biological property. Okay, you need to screen them. And next is there is no any presence of receptor molecule. Okay, so even if you do not have a receptor molecule, or if you do not have any information about receptor protein, then you can easily do pharmacophore modeling based on your active ligand molecule. Okay, so you can go and source the ligand molecule first. Okay, what can be the ligand molecule sets, or you can say training set, or you can say a simple library, and then you can align those ligand molecule, and then just by performing alignment, or you can say superimposition, you will get a basic idea about these features. Okay, so next is structure based. So in case of a structure based, you will have a protein molecule, or you can say a receptor molecule, and you will perform molecular docking here, and based on that complex structure, complex means you can say ligand with a receptor. Okay, or receptor protein. So once you get a complex structure, then you will screen, you will get a basic idea of, you can say, pharmaco features in that particular complex. Okay, the interaction pattern and all that thing would be there, and then based on that you can screen your molecule. Okay, so that is how structure based pharmacophore modeling actually works. Okay, and we can do structure based drug designing, or you can say structure based pharmacophore, structure based pharmacophore modeling, once you perform molecular docking through a structure based you can say approach. Okay, so this is a particular workflow for, you can say, receptor structures to pharmacophore modeling. So once you get a receptor structure, then you can perform this workflow to create your own model, pharmacophore model. Okay, first of all, you need to prepare a receptor complex. You can say the receptor with the ligand molecule. You need to prepare that complex. You need to load that complex into the solver, like Pharmit. We will be doing Pharmit later on. Okay, you need to upload that molecule into the you can say solver, or you can say there are a lot of software are available there, but they are commercially available. You need to have a, you can say, commercial professionals you can say license over there. So we are using Pharmit for this purpose today. Okay, and then you need to detect the protein ligand interaction, okay, contact, or whatever you call it. Okay, and then you will see the key features over there. Okay, within that particular source volume you will get the particular, you can say, interaction features, and based on that features you can easily build and then validate your model and screen the new compounds. Okay, screen new compounds from the data set, or even from your own library. Okay, so there are multiple tools, okay, we can use for structure based pharmacophore modeling. Like I've already told you, Pharmit. Okay, we'll be using Pharmit today. Okay, it's a free web based, you can say, structure based pharmacophore modeling tool. Okay, next is Ligand Scout, Discovery Studio. It's not Discovery Studio Visualizer in academic version. Okay, it's a paid version. You can get a professional suite over there. You can also call it a Discovery suite. Okay, and Schrodinger suite as well. Okay, so these are the softwares, and you can say servers that we can easily use to perform structure-based pharmacophore modeling. And in case of discovery or Schrodinger or ligand scout, you can perform, you can say, ligand-based as well. Okay, so Pharmit is especially for structure-based pharmacophore modeling. Okay. And in case of today's, you can say, session, we will be taking one QTI. Okay, in the right hand side, you can see GNT, galanthamine is a parent ligand present over this one QTI protein, acetylcholinesterase. Okay, so this has been docked over there, and then you can see a hydrophobic surface over there and a small dot present over there. It's a water molecule. Okay, and you can see a dot molecule. Okay, we will be discussing later on this, you can say, net-like structure. So these are specific pharmacophore features. Okay, we'll be talking about this later on. And this galanthamine is a co-crystallized ligand present over there, and based on the information of this co-crystallized ligand, we will be screening our own molecule. Okay, so we have already published an article about acetylcholinesterase inhibitors. So we will be letting you know what the you can say best inhibitor spatial position is. Okay, so from that information you will be getting idea about how pharmacophore modeling is important, and what is why it is so necessary for, you can say, for the drug screening. Okay, so in case of pharmacophore modeling, structure based, so first of all you need to load the receptor. So we will be loading one QTI which bound GNT into Pharmit. Okay, later on I will do that everything on Pharmit. Okay, and next is so if there are some kind of heteroatoms, or you can say cofactors, or even water molecules, then you can easily remove them. Okay, if you are sure that they have that kind of, you can say, non-active nature, then you can easily delete them. Or however, if you do not know the key feature of that molecule, or if you think like, okay, it plays an important role for biological stability of that molecule, then you should not delete that. Okay, the system will automatically take that into account. Okay, you can even go through, you can say, visualization tools like you can say Chimera, UCSF Chimera, or Discovery Studio Visualizer, or any other, you can say Pymol, or any other tools. Then you will see what are the cofactors present over there, what kind of molecules are present over there, and what is their, you can say, importance. Okay, so if they are you can say stabilizing the molecule, then you shouldn't delete this kind of you can say atoms. Okay, so, but if you think like, okay, it's away from active site, or if you think like it will block your ligand molecule to enter into the active site, then you can simply delete them and then work further. Okay, so in case of this particular you can say training workshop, will not delete water molecule, okay, that are present in active site of this one QTI. Okay, we'll not delete that, we'll keep it intact, and then we will perform pharmacophore modeling. Okay, so next is it will extract different features. Okay, hydrogen bond acceptor, okay, hydrogen bond donor, okay, hydrophobic aromatic rings, and all that thing will be generated by Pharmit itself, and then you will be screening them. Okay, which you can say pharmacophore structure is important for the analysis and everything. Okay, and then you need to define it as well. Okay, for example, if hydrophobic interaction are present over there in different positions, then you need to check each of them. Okay, to make sure that that is a major interaction. Okay, for example, in case of this particular compound, hydrogen bond donor, and you can say aromatic rings as well as hydrophobic interaction is very much important. So I'll be later on I'll be later on showing that through my own inhibitor as well. So these are the key features in this particular, you can say, receptor. Okay, so if I ignore that, then the pharmacophore model will be very weak. Okay, and then if I screen with that exclusion, then I'll not get a best result out of it. Okay, so you need to be sure about these kind of features. Okay, so if you have already performed molecular docking, and if you have got the best result, and even if you have performed molecular dynamic simulation, and if you are coming back to perform pharmacophore modeling, then it's very easier for you to understand the spatial features. Okay, but if you are doing pharmacophore modeling, and then if you are planning to go further for molecular docking and simulation, then you will not get a basic idea about how interaction would work. Okay, so you need to check each and every features over there. Okay, later on we will talk about it. Okay, don't worry. And then later on we will check that information with our ligand molecule. Okay, I've mentioned 5 different compounds. Okay, you can see this information on our published article. Okay, I'll not presenting each and every compound over there. the molecular docking thing and everything, but I'll be covering one compound, one best compound, and then showing how the interaction has been impacted, how the pharmacophore features has been impacted the you can say interaction in that particular compound. Okay, so that is what we are covering today. Next is this application of pharmacophore modeling. So the major application in drug discovery is for virtual screening. So I've already told you that virtual screening for the purpose of virtual screening, pharmacophore modeling is very important. Okay, it is crucial in you can say library preparation and screening those you can say millions of compound and getting the best compound out of it. Okay, so next is you can also design your new compound. Okay, that is what we call is de novo designing. So you can design your own compound. So once you get the best pharmacophore model, okay, you will get the idea about the special feature of that compound molecule. So based on that feature, you can easily screen that what functional group is important in the biological activity of that particular molecule. So you can easily edit that molecule. Okay, you can easily you can say derivatize that compound. Okay, derivatization can be performed from there, and then you can design your own ligand molecule. Okay, and then you can perform for the analysis. Okay, next is you can also optimize your compound to form a lead molecule. Okay, so you can do this after modification, several modification and testing onto you can say molecular docking, dynamic simulation, and even into the wet lab. Okay, and next is you can also take this information for ADMET screening. Okay, so as we have already discussed about okay ADMET analysis, because biological activity are you can say biological activity are key key parameters. Okay, with respect to this kind of ADMET features like absorption, distribution, metabolism, excretion, and toxicity. These are very much important to consider a molecule to be a drug-like nature, or even for the for the screening into the lead molecule. Okay, so you can design your own pharmacophore model, and then you can test ADMET, and then come back to derivatives and all that thing. Okay, you can do it you can say one by one, and then parallelly as well. Okay. So key takeaway from pharmacophore modeling is you shouldn't take this pharmacophore as a molecule. Okay, so think that it's a feature. Okay, that each and every active molecule needs to have that to be considered as a you can say biologically active molecule for further any kind of reference molecule. Okay, so that's just a pattern. Okay, it's not a real molecule. And next is ligand-based modeling is a right call whenever a receptor structure is not available. That means if you do not have any kind of receptor structures available, like for example, there are number of protein molecules that involve in repeated variation and mutation. Okay, so in that condition, you will not get a full 3D structure of your receptor. Okay, in that condition, you will be building your own homology model. Okay, and in that particular homology model, you'll not be getting any kind of ligand molecular taste. Okay, so in that case, you need to dock. Okay, you need to perform molecular docking and generate your own complex, and then come back to pharmacophore modeling, and then get the you can say spatial arrangement of your ligand molecule, and then you can test onto other molecules. So even if you do not have the structure of receptor, then you can do ligand-based modeling. Okay, and in case of freely available you can say web server, we have already discussed about Pharmit. So you can use Pharmit to prepare a model in case of structure-based drug design. Okay, in case of ligand-based, there is Pharmamist, but but it's not in full-fledged state right now. So we are not using Pharmist okay today, but later on, if it is function, then we'll be creating one tutorial for you and upload on our YouTube channel as well. Okay, and together, if you do QSAR docking and pharmacophore modeling from one complete CADD pipeline, then you will get the best result out of it. Okay, just by performing docking or QSAR or even ADMET analysis is not possible. Is not you can say is not sufficient for your entire study to be concluded in a short period of time. So if you combine these all techniques together, then you will screen. You can easily screen your molecule in a short duration. Okay, so that's it for the you can say basic presentation. Now we will be going on to Pharmit. Okay, and then we'll build our own you can say pharmacophore model. Okay, so this is it here. So if you have any kind of you can say queries, then you can let me know, or else we will be moving on to live demonstration. So I don't think you people have any kind of question. So let's move on to perform some kind of analysis. Okay, so let me use Pharmit. So this is you can say page, or you can say interface of Pharmit. Okay, so here you can see start from PDB. You can just type a PDB ID of your protein molecule, or you can upload your protein you can say complex molecule as well. I've already performed it, so I've already saved the session, so I'm not going to use this one here. Okay, you can just, for your information, for your queries, then you can just type the PDB ID of your protein. Okay, and you will get a bit. If you have a parent ligand, then here it will visualize your ligand molecule. Okay, and in the binding site water, if you want, then you can ignore water, or you can ignore other heteroatoms as well. Okay, or leave it default. Okay, they will do the thing. Okay, heteroatoms would be kept by Pharmit, or even if like if it is possible, then they can remove it and give you the result. Okay, so let me go through this inter-Pharmit search. Okay, so I've already saved the session, so I will be uploading that session and then letting you explore the features. Okay, so let's see. So this is the area where we can do our work. Okay, so you can see it's for virtual screening. Okay, you can easily you can easily screen your molecule from this tab, and you can see shape and everything. Okay, you can go and check out what you want to do here. Okay, you can reduce your heat number. Like for example, if you are doing virtual screening, then you can make it one or two for each heat molecule, or you can say if you are screening just one molecule, then you can just type one here, and then you can do it for the analysis. Okay, you can say alignment on all that thing. Okay, so you can also give your data here, like it's a admit parameter, so you can easily give the filters here. You can allocate molecular weight of whatever compound you are screening. So if you want a drug like compound from the virtual screening similar to your parent ligand, then you can allocate the molecular weight. Like for example, in case of admit analysis, the molecular weight needs to be less than 500 Dalton, right? So you can just click 500 Daltons. Okay, log p value less than 5. Okay, topological surface area, aromatics, hydrogen bond acceptor, donor, and everything. Okay, what we have already covered in our previous workshop as well. So you can use this value, you can use the guideline value present over there, and you can just source your heat molecule. Okay, and in case of visualization, like once you upload your complex molecule, you will be getting a complex molecule here. I haven't uploaded it. I want to load my sessions from here, so I'm just exploring it. Okay, I'm just explaining you the thing. So if you haven't saved the sessions, if you are doing for the first time, then you just need to go from the initial search. Okay, you just need to type the PDB ID of your complex molecule. Okay, there needs to be a complex. Okay, if you do not have a complex, then you will not get any kind of special you can say features of your complex molecule, your ligand molecule along with the complex. Okay, so you need to have a complex molecule first. You just need to upload there, and then you can come back here and then screen each and everything. Okay, so here you can see the ligand can be presented in different way, like a stick, from wire, from sphere, from a non. Okay, the results as well, you can define your result. In case of receptor as well, you can define whatever you want. And then in case of this means receptor backbone, you can make it plain or rainbow, whatever you want. Okay, later on we'll be exploring it, don't worry. So next is receptor surface opacity. That means you can create a surface over here. Okay, if you decrease this value, then it will create a surface. Okay, like a hydrophobic surface and all that thing, you can easily screen them. And background color, you can make it white or black. Okay, based on you can say the color contrasting and everything. You can adjust the background as well. Okay, and zooming feature and everything. So I've already saved the session of my 1QTI along with GNT galanthamine. So let me upload this. Okay, upload the session. So there it is. Okay, this is a file, JSON file. Okay, it gives a output extension of JSON. So you can just once you save your session, it will be resulting in that particular extension. Okay, so you can see this is a complex molecule. Okay, this is acetylcholinesterase. Okay, so let me go to PDB and you can get this molecule here. One QTI is the PDB ID of this molecule. Okay, so it's a acetylcholinesterase. Okay, obtained from Tetonica californica, and the homology is the sequence similarity it has a high sequence similarity with humans. So I have used this molecule for further analysis. Okay, so you can see it's a homodimer. Actually it can be appeared in monomer as well. So if you upload this structure on you can say visualization tool, you'll get a single chain. Okay, so you can just upload that single chain and then work on. Okay, you can get the basic idea of chemical features present over there, Ramachandran outlier, class score, and all that thing. So based on the guideline value, you can easily select the best protein molecule. Okay, so we have already discussed about the guideline value of how to select the protein molecule. Okay, how to select the receptor from the PDB. So you can go and check that as well. And later on, you can see a parent ligand GNT galantamine, which is a FDA approved drug. Okay, for neurodegeneration, especially in Alzheimer's disease. So this is a parent ligand. So based on the chemical nature of this galantamine, we can easily screen any kind of compound molecule. Okay, and fortunately this is a alkaloid molecule, and I've worked on 5 different alkaloid molecules. I've explored that alkaloid molecule from a local plant available in Nepal. So I've published this article based on the molecular docking as well as molecular dynamic simulation and so you can see admit analysis. Okay, so later on I will let you see that as well. So this is a protein. So I've uploaded this protein on Pharmit. Okay, so I've got this key feature of this galantamine. Okay, so you can see there's bubbles present over there. So let me show you what this bubbles actually indicates. Okay, so you can see the pharmacophore features are present over there, like hydrogen bond donor, hydrogen acceptor, okay, hydrogen bond donor, hydrophobic, hydrophilic, aromatic, or whatever thing. Okay, so let me see one bubble first. Okay, so this bubble indicates it's hydrogen acceptor. So here you can see from here a molecule can easily accept hydrogen bond, okay, with a protein molecule, or you can say with the amino acid residues present over there. So this is a key interaction for this particular galantamine. Okay, that means hydrogen bond acceptor. Okay? So you can expect hydrogen bond in this area. Okay, next is, let me see this green one. So this green one indicates it's a hydrophobic region. Okay, so in case of hydrophobic region, you can expect like pi interaction, pi sigma bond interaction in this region. Okay, so next let me explore this. So it indicates hydrogen bond acceptor. Okay, you can expect hydrogen bond from this region as well. Okay, next is this one. Okay, this is also hydrophobic interaction. You can expect hydrophobic interaction in this region. Okay, this is another hydrogen bond acceptor. You can expect hydrogen bond here, and you can get hydrogen bond donor. Okay, here 3 or 4 hydrogen bond donor and acceptor region are present over there. So you can get 3 or 4 hydrogen bond in this particular molecule. Okay, at least, or you can say maximum. No, just don't say maximum. Okay, so especially when they have worked on this particular galantamine, they perform molecular docking in galantamine with, you can say, acetylcholinesterase, and they have found 2 hydrogen bond, okay, with serine and glutamate. Okay, they are 2 hydrogen bond, and some kind of hydrophobic interaction are present over there. So I will present what I have got from my result, okay, later on. So this is the thing. Okay, so if I select this aromatic as well, so you can get I think this is the aromatic one. Is it? No, it's hydrophobic. So maybe this one, hydrophobic. uh, this one, sorry, this one is hydrogen bond acceptor donor, sorry. So where is aromatic? You can keep looking at looking to this bubble, and you can easily get the highlights over there, okay, to see what that the bubbles actually indicates. And these small molecules, red molecules, are water molecules, okay. They haven't ignored that. They have kept water molecule intact, thinking that they may form a water base, but in this case they are not so much important, okay. Maybe this one. No, it's hydrophobic. Hydrophobic. Too much features will also create a noise, okay. So you need to be very much careful about selecting these features. No, I don't know where is that aromatic. I don't think they have that aromatic feature here. Hydrophobic. Hydrophobic. Hydrogen acceptor. Okay, let it be. So next is, so you can work on this, you can play on this, and you can see what happens, okay. Like it has been presented in a black background, you can change into white, okay. And then you can change the receptor surface opacity, okay. You can get the, if you increase this opacity, you will get a hydrophobic surface, okay. Like this kind of hydrophobic surface will be generated, and you can easily see where this molecule is okay, interacting, okay. This is the hydrophobic surface of this molecule, okay. So let me decrease it, and then let me see what are the key residues, okay. Like, so from here okay, so this is the pocket, okay. This is the active side of this molecule, and then you can see, okay, although you cannot see the interaction because you need to perform molecular docking and then see the bonds and all that thing. However, it will give you an idea that where it can interact, okay. So from here you can interact, it can interact with other molecules. So let me do some, you can say, virtual screening from the library, okay. For example, you can see search molprot is one, you can say, database. So you can go through Campbell, molprot, chemspace, anime, okay, or many other databases, popchem, even popchem, and you can see the you can see the similar compounds, just like that of galantamine, okay. So if you want to do virtual screening from pharmacophore modeling, then you can just select that, okay. You can just need to select pharmacophore search to search filters, and then you can even load features over there, okay. And then if you are not if you haven't load any receptor molecule, then from here as well you can load the receptor, okay. So I'm going to search molprot right now, okay, and then see how many molecules are similar to that of galantamine, okay. So let me click here, okay. They are searching the similar kind of compound from molprot, okay. And they are screening this amount. This is the library, okay, of molprot, and they are screening 110, 100,000, 10,000, 100,000, 6 million compounds, okay. More than 6 million compounds. So from more than 6 million compounds, they have got 82,211,844 conformers, okay. Based on that conformer, now they will you can say screen out the best, you can say, confirmation of you can say the actual, you can say, active molecule, okay, similar to that of galantamine, okay. And then you can screen those compound, okay. You can get the information of that compound from molprot, you can download that and then do molecular docking further, okay. In this way you can use pharmacophore modeling for further drug designing, okay. Let me get the result first, and then we will be superimposing each of the hits, okay, each of the hits, to see whether they actually fit into this galantamine or not, okay. Let's wait for some time. maybe because we have selected a lot of pharmacophore features, that's why they are taking time. So you can reduce the search from here, and then it will give you result within some seconds. Okay, but let's see. Still they are searching for the best confirmation. Let me deselect them. Okay. Okay. Okay, you can see one molecule has been already there. Okay, and you can filter it from, you can see admit parameters and all that thing. So I've already told you about it. Okay, still searching. So let's wait for some second, and we can easily screen one of them. You can see RMST value. Okay, this RMST means root mean square deviation from the gallantamine. Okay, so if you superimpose, or if you see the if you superimpose two molecules, gallantamine and this particular mole prot conformation, then the RMST would be 0.525. That means it's quite good. So you need to select the lowermost RMST. Okay, so the lower the value is there, the biological activity would be greater, or you can say the best pharmacophore model will be prepared. Still searching, and once the search is completed, then you can see here in the shaded region minimize. So you can also minimize the energy of this particular conformation. Okay, and based on that you can easily select them. Okay, now they have given us 6 different conformations similar to that of gallantamine. Okay, so you can just minimize these structures. Okay, and they have got the score as well. You can see RMST value. Okay, so for this molecule you can see it has been superimposed perfectly. Okay, so it's the best confirmation. So if you want to perform molecular docking for this compound in in this particular receptor, then it is the best molecule. So in this way you can screen them. Okay, similarly second molecule. Okay, this where is it? This is not perfectly aligned. Okay, next. Okay, this is perfectly aligned, almost perfectly aligned. This is also fine. This is also good. This can be also taken into account, but the best one is this one. Okay, you can select this compound and further perform molecular docking. So and this way you can easily screen the compound. Okay, you can see everything has been perfectly aligned, and then the feature has been shared open these two molecules. Okay, once it is superimposed, and you can see RMST value present over there. Okay, so in this way you can screen the molecule. So previously we have seen, okay, although this gallantamine is still there, you can see hydrogen bond donor, hydrogen bond acceptor, as well as hydrophobic interaction are present over there. So once I perform molecular docking of my own compound in this particular receptor, in this particular site, I got the information. Okay, so let me share that information. If my compound has hydrogen bond as well as hydrophobic interaction or anything, okay, because it indicates hydrophobic indicates pi sigma bond or pi interaction, as well as hydrogen bond or donor and acceptor, it simply indicates hydrogen bond formation. Okay, hydrophilic interaction. So there needs to be hydrophilic as well as hydrophobic interaction from this particular region. So let me share you the information from my docked you can say complex. Okay, so this is the result of one of my potent compound. Okay, so it has been interacted with tyrosine and histidine. Okay, tyrosine and histidine to form a hydrogen bond present over there. Okay, so you can say tyrosine 1 to 1 and histidine 440. That means it has a hydrogen bond accepting, or you can say donating ability in this particular you can say substituent. Okay, and there is also hydrophobic interaction with tryptophan 84. So these three are key interaction for this particular ligand molecule. Okay, and histidine is already present in the catalytic region. Okay, and tryptophan, the interaction with tryptophan is very much important to form a pi sigma bond interaction. Okay, so it is very important for any kind of biological property, especially anti-acetylcholinesterase activity, or you can say acetylcholinesterase inhibition. Okay, and although the catalytic region has two more you can say amino acid residues like glutamate and serine, although I didn't get the interaction, however in the catalytic cleft histidine is present over there. Okay, so in the original literature they haven't reported histidine, however in my study I have found histidine as a key you can say residues to interact with my compound. Okay, so that's where you can report it. Okay, so I can share some you can say interaction of other molecules as well, like let me share it. Okay, so this is the most active molecule, and these are other molecules. Okay, that has been interacted by forming hydrogen bond as well as hydrophobic interaction. However, I have not taken them into further consideration. Okay, stephanin is the only molecule to have a most you can say inhibitory role, okay, among 5 compounds. Okay, you can see a lot of hydrogen bond as well as hydrophobic interaction for this particular molecule. So in case of ligand based, okay, in case of ligand based we can easily superimpose this molecule. Okay, superimpose galantamine along with my compound molecule similar to that of what I have performed from virtual screening. Okay, so we can do that and then calculate the RMST, but it has been already validated through molecular docking, so I haven't done this. Okay, you can do the similar thing. Okay, like if you do not want to do molecular docking further, then you can screen in this way. Okay, first of all make sure that you have this you can say a spatial arrangement first. Okay, and then you can screen number of compounds from different databases like MolProt or any other databases. Like you can see a lot of databases are present over there, and then from that database you can screen a lot of molecules. Okay, and then you will get the best heat present over there, and then you can just superimpose, and then you will get the best result out of it. Okay, so in this way you can perform pharmacophore modeling to get the basic feature of your ligand molecule, okay, to carry further for any kind of biological activity. Okay, so this is it for basic modeling. So if you want to involve in any kind of project work, or if you are searching for any kind of project work and then improve your skills, then we can organize any kind of you can say internship or workshop further. Okay, paid one, and then we can train you for at least to a month, and then you will be able to screen your compound molecule. Okay, and to lead in into a best possible you can say project. Okay, so in this way we have ended this particular workshop today. So if you have any kind of queries, then you can let me know. Okay, thank you. Okay, if there is no any questions, then we can stop, you can finish it. Okay, is there any question? I think there are just few peoples, so I have stopped sharing it. Okay, so okay, so you can go back to the YouTube and then okay, trace back whatever we have done. Okay, and then you can get the information over there. Okay, so this is it for today. So in the next session we'll be organizing similar kind of modeling. Maybe most probably we will be doing homology modeling in the next session, and then we will keep uploading you can say drug designing tips and tips every day. Okay, we have been doing it for past 1 month. Okay, so you can go and get the information about this kind of thing in our YouTube channel as well. Okay, so this is it for today. Thank you for attending it. So thank you.